Okay, so a few students have had a little bit of difficulty with questions like this, and it's because of the form of the question up here. So if we don't like the form, the idea is to change it into a form that we will like. And we do that by doing a short division. So we get 2x minus 1 is divided into x plus 3. What do we need to multiply 2x by to make it into x? A half. So we multiply a half by that, that gives us x minus a half. We do our subtraction, and that gives us 3.5, because 3 take away negative a half is 3 plus a half. Now 3.5 can be written as 7 over 2. So we can now say that x plus 3 over 2x minus 1 is equal to our half that we got here plus 7 over 2 over our 2x minus 1. Now, if we simplify this a little bit further, we can write this as a half plus 7 over 2, 2x minus 1. Now, the reason why you want to do this is because now you can determine what the range of this is equal to. So, since it looks like it's a hyperbola, which it definitely is, that means our horizontal asymptote is going to be y is equal to a half. Meanwhile, we already knew from our denominator that our vertical asymptote was going to be x equals a half. Now we can draw up a little domain and range table. So we've got domain and range. Let's just put f and f, even though it doesn't make a whole lot of sense. But as it turns out, the domain of f was r except a half. Squiggly brackets not going in properly. And the range was r except a half. Now, if we want f of fx to exist, what we want is the range of the inner range of f to be a subset of the domain of the outer. Well, as it turns out, they're equal to each other because both of them are r except for a half. So that is a subset of r except for a half. Therefore, fx exists. And that answers the first part. So now what we're going to do is part B. Now part B asks us to find f of fx. Now I think it's a little bit easier using the original version of the rule here. So we're going to try and find out f of x plus 3 over 2x minus 1. Now, when we sub this in, we've got to be very careful. So the top x gets replaced by what's in the brackets, x plus 3 over 2x minus 1, and then we write plus 3 at the end. This is all divided by 2 times whatever was in the brackets, and that's the x plus 3 over 2x minus 1, close brackets, and then at the end we've got this minus 1. Okay. Then we need to put everything over the same denominator. So that 3 needs to go over a denominator of 2x minus 1. So we're going to multiply the top by 2x minus 1 and the bottom by 2x minus 1. That means what we've got is x plus 3 plus multiplying out, we get 6x minus 3. That's all over 2x minus 1. Now on the bottom line we're going to be dividing by this part here. So we need to expand the top line. That's going to be 2x plus 6. And we're going to try and do the same thing with putting this over a denominator of 2x minus 1. So we're going to make this minus 2x minus 1. And that's all going to be over 2x minus 1. Up here, this becomes x plus 6x is 7x. Oh, plus 3 minus 3 is 0. That's a nice one. Over 2x minus 1. Here we're going to change the divide into a times. So we're going to use the stay, change, flip, and that means we're going to flip this fraction upside down. That makes that 2x minus 1 on the top, and on the bottom we've got 2x minus the 2x, oh that's 0. And then we've got 6 minus negative 1 is 7. Oh, look at this, things are going to cancel out here. So the 2x minus 1 cancels the 2x minus 1, the 7 cancels the 7, and that means you've got x. So the answer to part B is just, well, it's just x, isn't it? Now, when we draw the graph, we need to be careful that we remember that the domain of fx is the domain of the inner function fx. Now remember, up the top we knew the domain was r except for a half. So we draw our straight line like so. However, when we get to a half, we need to put in an open circle. You're not going to need to put a rubber in there or an eraser. So that's going to be an open circle there because we're not including that point. And apart from that, part B is now done. And so we saw in the previous slide that the answer turned out to be x. So it's probably a good idea to talk about what your calculator can and can't do for you right now. So you can actually use your calculator to define what the function is equal to. By the way, if you don't know where define is, look in interactive and the drop down menu, you'll see the word define, and you just put in the expression for what fx is equal to. So here I've defined fx to be equal to x plus 3 over 2x minus 1. That's the same as the one we had up there, so there's no drama. And then I've tried to ask you to work out f of fx, and it's served this up to me. Well, it's actually correct, but it's not really what I want. So on the next slide, I'll show you what you can do about that. There is a function inside the calculator which actually simplifies expressions such as this, and that's the function called simplify. You'll find that if you click on interactive and you go to transformations, and then you'll find simplify in there somewhere. And it's actually quite a powerful tool because it takes this thing, which is quite unwieldy, and it converts it into its simplest form, and there's that answer we got before, which was x. So it's quite a nice little thing the calculator does for us. And so we get to the last part. This turns out to be the easiest part because we know that if f of gx equals gfx, which is equal to x, then we can say that fx is the inverse of gx. Well, in this question it's even easier because we already know that we're finding f of fx. So we can say that fx is the inverse of fx. Oh, what that means is we've already got the answer sitting in front of us. Therefore, the inverse of fx, i.e. f minus 1x, is equal to x plus 3 over 2x minus 1. Okay, that one was easy, wasn't it?